Welcome to day 13 of our 15-day beginner data science series. In day 12, we created our first classification model. Our model tried to predict whether a student was at risk of failing. But creating a model is not enough. We also need to know whether its predictions are useful. Today, we will learn how to evaluate a classification model correctly. We will understand accuracy, precision, recall, F1 score, confusion matrix, classification report, and magnetic class baseline. Do not worry if these terms sound technical. We will understand every metric using a simple student example. Our opening question is, can a model be 95% accurate and still be a bad model? Surprisingly, the answer is yes. A model can appear highly accurate while completely failing at the task that matters. By the end of this lesson, you will be able to explain not only how often a model is correct, but also what kinds of mistakes it makes. Open Google Colab and click on New Notebook. Rename the notebook as day underscore 13 underscore evaluating underscore models underscore correctly.ipinb. This is a completely new notebook. Therefore, we will repeat the important setup steps from day 12. We will import the required libraries, load the dataset, create the target, select the features, split the dataset, train logistic regression, generate predictions, and evaluate those predictions. Repeating these steps is useful because the data science notebook should clearly show how the result was produced. In the first code cell, import the required libraries. Pandas will help us work with the dataset. Matplotlib and Seaborn will help us visualize the confusion matrix. Now import the machine learning tools. Train test split will divide our data into training and testing sections. Logistic regression will create the classification model. Now import the evaluation tools. We will understand each of these functions during the lesson. So on running the cell, there should be no output. That is normal. Importing a library only makes its tools available inside the notebook. We will use the same student performance dataset that we used for our earlier lessons. Open the file section on the left of Google Colab and click on upload button. Upload student performance classification.csv. After uploading the file, load it using Pandas. Before running the cell, predict the output. Will Pandas show the entire dataset? No. The head function normally displays the first 5 rows. Run the cell. Our dataset may contain columns such as study hours, attendance, previous score, sleep hours, assignments completed, participation, and final score. Each row represents one student. Each column describes something about that student. Let us check the size of the dataset. The first number tells us the number of rows. The second number tells us the number of columns. Now inspect the column names. This step is important because we need to use the exact column names while creating the model. Let us also inspect basic information. This tells us the column names, the number of non-missing values, and the data type of each column. For this lesson, our model requires numerical features. A classification model predicts a category. Our dataset currently contains a numerical final score. We will convert it into a category called at risk. Let us say that a student is considered at risk when the final score is below 50. Let us understand this carefully. The condition DA final score less than 50 produces either true or false. The hash type int part converts true into 1 and false into 0. Therefore, at risk equal to 1 means that the student is at risk, and at risk equal to 0 means the student is not at risk. Display a few rows. Before running the cell, predict the result. A student with a final score of 45 should receive which class? The answer is 1. A student with a final score of 70 should receive which class? The answer is 0. Run the cell and verify the result. Before training the model, let us count the number of students in each class. This tells us how many students belong to class 0 and class 1. Let us also display proportions. Suppose 65% of the students are not at risk and only 35% are at risk. This means the classes are imbalanced. One class appears much more frequently than the other. Class imbalance matters because a model may achieve high accuracy simply by predicting the majority class repeatedly. We will see this problem later in the lesson. Features are the input columns used by the model. The target is the column we want to predict. Let us select the features. Now create capital X and Y. Capital X contains the inputs, Y contains the answer that the model is trying to predict. Notice that we are not using final score as an input. Why? Because at risk was created directly from final score. If we use final score as an input, the model would indirectly receive the answer. That would be data leakage. Data leakage makes model performance look unrealistically good, but in actual it is not. We will divide the dataset into training and testing sections. Let us understand each parameter. Test size equal to 0.2 means that 20% of the data will be used for testing. The remaining 80% will be used for training. Random state equal to 42 makes the split repeatable. When we run the notebook again, we should receive the same split. Stratify equal to y tries to keep a similar proportion of at-risk student in both the training and testing data. This is useful when the classes are imbalanced. Run the cell. Now inspect the sizes. The model will learn from the training data. We will evaluate it using the testing data that it did not use during training. Create the model. Now train it. Before running the cell, ask yourself, will the model produce predictions immediately? No. The fit function only trains the model. Run the cell. The model has now learned patterns connecting the input features to the at-risk target. Now let us generate predictions for the testing data. Display the first 10 predictions. The output contains zeros and ones. 0 means not at risk, 1 means at risk. Let us compare the actual and predicted values. Some rows may match, some may not. The rows that do not match are the model's mistakes. Today we will study those mistakes carefully. Every prediction belongs to one of the four categories. Let us understand them using our student example. So the four possible outcomes. First is the true positive. The model predicts that the student is at risk. The student is actually at risk. The prediction is correct. This is called a true positive. Second is the true negative. The model predicts that a student is not at risk. The student is actually not at risk. The prediction is again correct. This is called a true negative. Third is false negative, false positive. The model predicts that a student is at risk, but the student is actually not at risk. This is called a false positive. The model has created a false warning. Fourth is a false negative. The model predicts that a student is not at risk, but the student is actually at risk. This is called a false negative. The model has missed a student who may need help. Think about the consequences. A false positive may cause a teacher to check on a student who did not actually need intervention. A false negative may cause an at-risk student to receive no support. In this particular use case, a false negative may be more serious. This is why we need more than one evaluation metric. A confusion matrix count the four types of outcomes. So let us print the confusion matrix. Before running the cell, predict the shape of the output. Because we have two classes, the output should be a 2 by 2 matrix. Run the cell. The matrix follows this structure: true negatives, false positives, false negatives, then true positives. So true negatives is on the left top and true positives on the right top. False negatives on the right, true positives on the right bottom. False negatives on the right top. This is the false positive and this is the false negatives. The rows represent the actual class. The columns represent the predicted class. Let us extract the individual values. Now the result is easier to interpret. The most important value may depend on the problem. For our student support system, we should pay close attention to false negatives. False negatives are students who were genuinely at risk but were missed by the model. Let us display the confusion matrix as a heat map. Let us understand the arguments. And not equal to true displays the numbers inside the boxes. FMT equal to D displays the numbers as whole numbers. The horizontal axis shows the predicted classes. The vertical axis shows the actual classes. Before continuing, pause and identify the true positive box, the true negative box, the false positive box, and the false negative box. Do not judge the model only by looking at the darkest box. A class with more observations will naturally produce larger numbers. Let us calculate accuracy. Accuracy answers out of all predictions what percentage was correct. Its basic idea is correct predictions divided by total numbers. Divide total predictions. Suppose the accuracy is 73%. That means the model made the correct class prediction for 73% of the test students. But accuracy does not tell us which students were classified incorrectly. It does not tell us whether the model missed the at-risk students. That is why accuracy should not be used alone. Imagine that we have 100 students. Out of them, 95 are not at risk and 5 are at risk. Now imagine a model that predicts that every student is not at risk. It correctly predicts the 95 students who are not at risk. It incorrectly predicts the 5 students who are at risk. Its accuracy is still 95%. That sounds excellent. But the model did not identify even one student who needed help. Therefore, high accuracy does not always mean that a model is useful. We must compare the model against a simple baseline and inspect other metrics. Calculate precision. Precision asks when the model predicts that a student is at risk, how often is it correct? The basic formula is true positives divided by all projected positives. All predicted positives. So the basic formula is true positives divided by all predicted positives. Suppose the model flags 10 students as at risk. If 8 of those students are genuinely at risk, the precision is 80%. High precision means that the model creates fewer false alarms. Precision becomes important when false positive predictions are costly. Now calculate recall. Recall asks out of all the students who were genuinely at risk, how many did the model find? Its basic formula is true positives divided by all actual positives. Suppose 10 students are genuinely at risk. If the model identifies 7 of them, recall is 70%. High recall means that the model misses fewer positive cases. Recall becomes important when false negatives are costly. In our student support system, recall may be especially important because missing an at-risk student could prevent that student from receiving help. Now calculate the F1 score. The F1 score combines precision and recall into one value. It is useful when we want a balance between avoiding false alarms and finding real positive cases. A high F1 score normally requires both precision and recall to be reasonably strong. However, the F1 score should not completely replace precision and recall. Two models can have similar F1 scores but make different types of mistakes. Always inspect precision and recall separately. Let us display the four metrics together. So these numbers are usually different. Do not choose the metric with the highest value just because it makes the model look good. The real world use case should determine which metric matters most. So let me repeat. The real world use case should determine which metric matters most. Scikit-learn can display the main metrics in one report. The report shows precision, recall, F1 score and support. Support means the number of actual examples in each class. So let me write it because it is referred very often. Support means the number of actual examples in each class. Focus especially on the at-risk row. That row tells us how well the model handles the students we want to identify. The report may also display macro average and weighted average. For now, the main rows to understand are now at risk, not at risk, and at risk. A model should be compared with a simple baseline. A majority class baseline predicts the most common class for every student. So let's import dummy classifier. Create and train the baseline. Calculate its accuracy. The model does not learn useful relationships. It simply predicts the most frequent class. If our model cannot perform better than this simple baseline, we should question whether it is learning anything useful. However, do not compare only accuracy. The baseline may achieve high accuracy while having zero recall for the at-risk class. Display the baseline classification report. Now compare it with the logistic regression report. The majority baseline may have reasonable accuracy, but it may fail to identify any at-risk student. Our trained model should ideally provide value beyond that baseline. So it is for at-risk student the precision is 0, recall is 0, and accuracy is 0.64. And for our model, the precision is 0.67, recall is 0.55, and accuracy is 0.74. So we did good in the recall value. Pause the video here. Look at the confusion matrix and evaluation matrix. Explain the most important result in one sentence without using technical jargon. Do not simply write recall is 0.75. Instead, write something like the model found 3 out of every 4 students were genuinely at risk, or most students flagged by the model were genuinely at risk, but it also created a few unnecessary warnings. So in our case, we almost found one of the two the people who found we found to be the person at risk. Only half of them were really at risk. That could be the one sentence explanation. This is an important data science skill. You must be able to translate model metrics into everyday language. So this is not at risk and at risk. We need to consider at risk because we want to get the recall value of at risk student. Was it able to was the model able to find all the at risk student? So it only found only half of them. Now complete today's challenge. So this is the today's learner challenge that you need to complete. You have two situations. Situation one is disease screening, and situation two is spam filtering. So a model predicts whether a person may have disease. Think about what happens when the model incorrect incorrectly says that a healthy person may have disease. Second, what happens when the model misses a person who actually has a disease. And third, should precision or recall receive more attention based on the above two answers. Situation 2 is spam filtering. A model predicts whether an email is spam, and you have to think about what happens when a normal email is incorrectly sent to spam. What happens when the same spam email remains in the inbox? Should precision or recall receive more attention? So these are the two cases. Let me format it properly so that it becomes easier to read. Write one or two sentences for each situation. Pause the video and complete the challenge. For disease screening, recall usually deserves more attention. Why? Because a false negative means that a person who actually has a disease is missed. This could delay further testing or treatment. For spam filtering, precision often deserves more attention. Why? Because a false negative means that a legitimate email is incorrectly sent to the spam folder. The user could miss an important message. So these are not universal rules. The correct metric always depends on the consequences of the mistakes. So a common mistake is to calculate several metrics and then report whichever number makes the model look best. That is not the correct approach. The metric should be selected based on the use case before judging the model. Let us recap. Accuracy tells us how many total predictions were correct. Precision tells us how often positive predictions were correct. Recall tells us how many real positive cases were found. The F1 score balances precision and recall. The confusion matrix shows the four types of prediction outcomes. The majority class baseline helps us determine whether the trained model is better than a very simple strategy. For our student support model, recall may deserve extra attention because missing an at-risk student may be more harmful than checking an additional false warning. However, precision also matters because too many false alarms may reduce trust in the system. Your final learner evidence is one sentence. I would prioritize dash because dash. For example, I would prioritize recall because missing a student who genuinely needs help may be more harmful than reviewing an additional warning. That completes day 13 of our data science series.